Welcome everyone to this webinar on the grain drain, large-scale grain port optimization. It's really exciting to be here tonight. Looking forward to a great presentation. I'm going to be sharing a lot of really good insights with everyone. For those of you who are looking really to get into the deep technical mathematics of this and how we interface exactly with Gurobi, that's not going to be the purpose of today's talk. What I really want to show people, and I think more than anything that the technical people benefit the most from this, is how do we solve a complex mathematical problem, something that's extremely challenging without delving deeper into the mathematics. So what is there within the problem itself that we can sometimes use that's quite surprising that help us solve difficult mathematical problems, difficult optimization problems in the field? And today you're going to learn all about how we do that. So with that being said, let me get started and introduce the problem to you. The problem that we're looking at here is one of a supply chain issue. Within the grain market, when transporting and harvesting the grain and getting it to the port and taking it to its final end user, supply chain costs can contribute roughly 30% of grain production costs. That is up to about $75 a tonne. That begins with the farmers farming and planting and getting the grain to the point of harvesting it. Then they harvest it. And once they begin harvesting it, they need to then transport it to certain central locations so that it can then be transported onward to the facilities to process that grain. And within Australia, where I'm calling from tonight, that typically means the grain that's coming from Western Australia moving to ports somewhere around Perth, and the grain from Victoria region moving somewhere around Melbourne. And if you imagine in your head millions of tons of grain being transported to these ports, you can understand where the bottleneck's going to be. And in fact, as you see at the point in the bottom, the efficiency of the port is actually the major driver of these costs because it's where all this enormous amounts of grains converge. Once the grain hits the port, then you have what's called blending. So we need to blend the grain to achieve certain characteristics, typically those characteristics being around certain protein levels. For example, 10% protein level within a grain supply that's used for a specific purpose. And what we need to do is we need to blend the different products that are arriving via trains and via trucks and all sorts of other methods to the final output that's then put on the ship and sent to the final consumer of the grain. So it's quite a large-scale process. It involves a lot of moving parts, but the key bottleneck, the key part of it, is at the port. Now, clearly, this is a really important thing. This is something that basically feeds the population in most of Western society. We're a huge consumer of grains in all its variety of forms, and basically grain itself forms the basis of many of the products we use. So if we reduce the costs within that supply chain, if we can achieve some type of significant cost reduction by tackling those bottlenecks, it'll have large flow-on effects in society. And even more so important, if we really want to know the real reason why we do this job and improve those costs, is because these grains are a key component of beer. So next time you go to the pub and you're getting a 10% off and the price is going down, you can thank Biarri for optimizing the port and the blending and the transportation of grain to your final cup of beer that you get at the pub. So it's a really key process, this grain management and getting it from those farms into your cup of beer or on your plate as a piece of bread or some pasta. However, it doesn't stop there. The problem itself is fascinating because it actually forms the basis of many different types of optimization problems in supply chains, in multiple industries. For example, in the mining industry, you have the mine planning and setting up the mine. Then you process and refine those resources before you transport them again to a specific location like a ship or a port before it then gets transported off overseas. And you have that same process of taking it from the mine, transporting it down, blending it, and then loading it onto a ship before it gets shipped off to its final consumer and the end user who then value adds to that product. So it's an amazing problem, very general, and the tips and the tricks that I'm going to give you today, the insights to help your problem. And these are going to be more from the business perspective and not the mathematical perspective. But what's clever about this is these business perspective I'm going to give you translates directly into a simplification of the mathematics and an improvement of how we actually model the whole problem that I'll show you led to a major breakthrough in how we solve this. So that being said, let me jump into the actual mathematical problem that we were facing at a higher level. I'd like to describe a little bit what it is that we're looking at. So the problem we're looking at is actually a multi-commodity network flow with blending. It's known as the pooling problem in the literature. Now, at a high level, we use an MIP, a mixed integer programming solution, in a very similar way to a typical multi-commodity network flow. But what we do is we allow arcs between nodes where the product can transform type. So that means instead of having this conservation of type between nodes, if we have something in a location, for example, in a silo, that's being transported to another silo, it might be that, for example, the protein content in the first silo has 10% and the protein content in the next silo is 8%, but we're blending things to reach that 8% level. And I'm going to show a slide that visualizes that in a bit more detail to help you understand it. What we need to do is when we're transporting things around, we need to enforce that the right mix of product has been transformed. So that's a type of conservation that occurs between the different characteristics in the silos that will be transported. But ultimately, we did away with the nodes in our formulation, and it may help to think of there being one node for each silo, time step, and commodity combination, and an arc from nodes at time step t to time step t plus 1, even though we removed this, we abstracted away this idea of a node. But to visualize it and help conceptualize it, it helps to imagine in your mind, and it looks something a little bit like this. So at time t, you'd have a set of silos with different characteristics here, those characteristics here being certain percentages. And then at time t plus 1, we transport grain between those different silos. And the condition down the bottom, the constraint, is that we have cross-commodity protein limits, in our specific case of grain, so that the protein composition of the outflows from a set of silos is equal to the required protein grain of that silo. And again, you can see the general nature of this problem. It's very generic, and it really allows itself to be applied in a wide variety of industries. It's a really powerful framework. And the power that it brings and the optimization advantages that we'll see later on were very significant. So let me get into a little bit of the practical details, because this is actually the key to the problem. If you pay attention over these next few slides, you'll pick up probably one of the key takeaways that I want to give everyone tonight when solving optimization problems. And the key takeaway is really about understanding the business problem deeply, because it'll give you mathematical tricks in your toolbox later on that any deep mathematical theorem won't be able to give you. So the client that we're dealing with has something that looks a little bit like this. It's not exactly this, but it was similar to this, where they had a 12-floor silo building and they had 1 million tons of storage on site. It was a huge facility. It's one of Australia's largest. They had this really interesting thing. It's called the Mad Mile, and it's 700 meters of belt out to the vessels, and the belt runs only one way. If a piece of grain lands on that belt, that's it, adios. It's going out to the ship, and it's going to land on the ship. Now, from a mathematical perspective, that's not very relevant, because whether the ship's at the end of the Mad Mile or next to where actually the grain's located, that final delivery, once it's occurred, it's occurred. You could imagine that once it hits the belt, it's on the ship. However, there is an important part of this in that it adds to the cost and just the fact that it looks really cool. This crazy long bridge that goes out to the ship, it's about 700 meters long. It's not specifically this one. This one's at Port Lincoln in Australia, but it was also an interesting part of the problem that helped understand the challenges that they were facing, and in particular what they saw as important. Another really interesting part of this problem, this totally blew me away, and it was really interesting when this was revealed, is that the client actually also used the space between the silos as cells. So not only were they filling up the silos, but see that space in red, they were filling that up with grain as well. Now, They didn't have an open facility like this, because if you filled that up with grain, it'd be free food for the local wildlife. But in their case, it was a closed facility. And you can imagine, as a mathematician, if you look at that and see all that wasted space, you too would think, I've got to do something with it. So in the end, they actually also filled up the annexes, bulkheads, and all the space in between. And in total, had around 254 silos storing over 1 million tons of grain that was supplying the world with wheat and other products. Those silos themselves are connected via a complex network of lifts. Now, the previous slide and this slide here are two little hints to something that's going to come later on that's going to simplify our problem significantly. And this complex network of lifts, it's joined in ways that you need to be able to model to understand what can be transported from where to somewhere else, and how you can abstract that to take away the practical details and stick with actually what matters in terms of transportation between silos. However, what's essential here is that we need to have and understand the way these lifts and also conveyor belts are connected. Because it's not just that there's one conveyor belt from silo A to silo B. What can actually happen is you can have silo A and B connected with a conveyor belt, but halfway along that conveyor belt, a conveyor belt from silo C is joined. So you can send material from silo A to silo B, and you can send material from silo C to silo B, but the final section of the conveyor belt is shared. And this was a key issue that we needed to pay attention to when modeling the problem. Otherwise, we would have come up with unrealistic solutions. So the scale of this problem is roughly the following. We have 50 million tons of product moved, the majority through the closest port. So you're not going to take product from one state in Australia and send it to another state to find a port in a different state. You're going to find the closest port, and that's a restraint and a restriction on what you can or can't do. We have oats, we have lupins, we have all sorts of grains like wheat and sorghum and stuff like that, as well as barley and canola coming into these locations, and they all need to be managed separately. So if a belt's used for wheat, it needs to be cleaned before it can be used for canola. Otherwise, we're going to have cross-contamination between the products. The product itself is pushed onto the port, and we must accept all product delivered and only decide how product is moved within the port, within the storage facilities. Labour and electricity power bills are still two major cost drivers at the port, and we wanted to minimise these costs. And this was a fantastic optimisation problem, because when we walked in the door, we found out that 60% of product is moved more than once. It's touched at least twice. If you as a mathematician or someone in operations research were to see that, you'd see automatically an opportunity to optimize it and try and remove that 60% of multiple touches of the product to then minimize the costs and electricity and staffing associated with that. In particular, some realistic and practical constraints, so it wasn't just a matter of moving around grain. We had to schedule fumigations, we had to schedule cyclical cleaning and preventative maintenance. And the final point, and this will come back to perhaps some questions that we may have later on around stochasticity and stuff like that, was that we had target type proteins levels to the nearest 0.1%. And this impacts the commodity count and what we can actually do with the different grains in terms of blending them and mixing them. From a mathematical perspective, it may not be challenging. However, we need to build in the fact that this algorithm needs to be practical and used by people. So they need to trust that the final output is within that 0.1% from the practical implementation perspective of the actual optimization algorithm. So what does this problem look like? How big does it get? How big can this practical problem get? It can get this big. So again, doing away with nodes in our formulation and thinking of silos, time steps, and commodity types, what do we have? We have roughly 260 silos by 260 silos, so you can get one product from one silo to any other silo, over a 4-week horizon, so 7 days by 24 hours by 4 weeks. And for each commodity type, that's 13 minus 8, that's just the way it's counted, times 10 plus 50, gives you 4.5 million variables. Now, if you just take a problem like this and think, I'm just going to throw that into Gurobi, you're probably going to blow up the server that Gurobi is sitting on. Because not only do you have that, you have staffing, you have fumigation, you have cleaning, you have maintenance, and a whole variety of other things. The size of this problem just from the variable side is going to be too big. An example, just to show you practically what one of those pieces look like, and from the fumigation perspective, is this. This is what actually that fumigation element looked like that we needed to consider. And when we're coming into the constraints, which was the next part of the problem, we needed to add things for the fumigation around the arc generation and a number of other aspects. So this is how we manage that aspect. And in addition to those 4.5 million variables, you're adding complexity on top of it, such as this. So that leads us to actual formulation of the problem. How did we formulate the problem in such a way that we were able to, first of all, create what you could call a minimum viable problem? So the first version of the problem, the first cut, how can we get something that makes sense and it works? So then that we could build on that problem and optimize it and build something that then at the end of the day was able to function according to the specification of the client. So as I mentioned in the beginning, I'm not going to go deep into the mathematics here because I want to reveal a few insights to you around how we solve the mathematical problem from a much simpler perspective, something that's much, much easier than trying to identify specific mathematical properties of the problem that lead to a better solution. And I think that will be something that you'll be able to use in your own problems to simplify the challenges that you're facing. So at its core, we need to define the sets. What are the variables of interest within our mixed integer program? Those are things like time periods, they're things like commodities, so the different grains and stuff like that. They're a set of buckets, and buckets is our generalized term for a silo, an annex, a bulkhead, a variety of other things. We have a set of vessels, so they're the ships that are going to get loaded with the commodities, a set of shifts for the workers, so when the workers work, because you need to make sure that there are workers capable of managing what we've put in there. We have a set of nodes, and the nodes are composed of time periods, commodities, and buckets, but again, we abstracted them away, so we're thinking of them as part of the optimization problem. We have a set of arcs, and they're the abstracted conveyor belts that are grouped together. Now, within those conveyor belts, we have the thing that I mentioned before around different conveyor belts being connected in interesting ways from a topological and geometrical perspective. So we needed to make sure we captured that within the problem. We also had a set of incompatible arcs, and that's around that path shared by a conveyor belt, as I mentioned earlier. If path from B to A to B is being used, we can't use path from C to B if it shares a conveyor belt. And then there was a really interesting final aspect to this, and that aspect was priority-dependent buckets. Priority-dependent buckets was around the idea that some of the silos or the bulkheads or the annexes had special properties where what you could do is you could deplete or remove a large portion of grain from them, right down to perhaps 10% capacity. But at the 10% capacity, that method that you're using for the removal of grain no longer was effective, and you needed another way to remove the grain. It could have been a person going in there and manually removing the grain. And so we had to have this priority dependency in the buckets where we had silos with different emptying strategies. And those 9 aspects comprise the set of variables. The next most important thing, or equally important, is the objective function. So the objective function that we had was something that's probably not very complicated, and again, the insights I'm looking to derive here aren't necessarily in the mathematical formulation. It's in the tricks we apply to it to get those 4.5 million variables down from something intractable to something that we could work with. And that objective function was defined as minimizing the cost of all port operations, including active operations, staffing costs, and demurrage costs. And those demurrage costs are the costs involved with having a ship wait. You don't want a ship to sit in port, not doing anything, waiting to be loaded. If we turn that kind of at a high level into a mathematical formula, that is minimize the arc fixed costs, plus the arc variable costs, plus the staffing costs, plus demurrage costs. And most of those costs that we've discussed so far are in those arc fixed costs and arc variable costs. And what those arc fixed costs are is they're things like there's a fixed cost just simply to use an arc, to use a conveyor belt between 2 locations. And you just have to pay that every time you switch that conveyor belt on. But there's an arc variable cost as well, and that is due to things like the amount of grain or product on a conveyor belt requires a different amount of electricity to drive it and a different amount of other aspects of the production facility to actually, and the port facility to actually manage that. So there are variable costs. And so what we had was both continuous variables for the arcs for quantity and binary variables to indicate usage to handle the fixed costs. So we actually had continuous and binary variables in there to manage those two styles of cost. So again, I don't think there's going to be any deep mathematical insights out of that. This is kind of the problem, and it's hopefully relatively straightforward and understandable by the audience this evening. The next part and the final part that defines our MIP is the set of constraints. And we have a variety of constraints to reflect the most important parts of the problem, such as arc capacities for the used arc, so how much can we transport on this conveyor belt or in these different lifts. We have node capacities with inflow, so how much can this silo actually take. We have the usual flow conservation properties, so that normal flow in equals flow out. We have arc group usage, tonnage, and timings. We want to prevent the mingling of different commodities. Closing profiles, which is the status of inventory at the end of the sold period. So at the end of a 4-week period, we need to know what that profile looks like. It needs to match something specified at the beginning. Vessels are filled with pre-ordered goods and so forth. So there are also a variety of other less important constraints, but these three things, those sets, the objective function, and these constraints basically define the optimization problem. This is what we're looking at. However, just like Flash Gordon here, as we started adding more and more of those variables, as we began with something small and started modeling the problem and increasing the number of variables, and we hit that 4.5 million mark, all of a sudden, our optimization engine wasn't going anywhere. Our problem had become too big and complex with 4.5 million variables and thousands or tens of thousands of constraints. We've reached the point where Gurobi's going to break. And we recognized even on the first instance where we'd create that minimum viable problem and we ran it, that Gurobi just wasn't able to hack it because it was simply too big. So now the challenge was on. What could we do? At this point, as a mathematician, you'd be typically faced with a number of choices. And one of those choices is typically something along the lines of, why don't we look at the mathematics of the problem and dig deeper and try and figure out what are the mathematical properties of this? What does the solution space look like? How does the objective function relate to that solution space? Can we do some type of decomposition of the problem into specific parts and solve it like that? And you typically look at all these mathematical methods. But what happened at this point was it was our visit to the site and our discussions with the people who run the operations that actually led to a deep insights as to how we could solve this thing efficiently and change the problem into something much, much simpler. And this understanding was only gained by talking to the business. Now, this is what I really want everyone to take away from this speech, is this understanding that we gained. And I want to go through some of the speed ups here, and particularly focus on some of them that you'll see came from that business understanding. So a lot of the successful speed ups that we tried were things around arc culling. So if they had the same silo type, there's no point in moving grain between them. We also had arc culling blending to non-ordered products, so that order in terms of delivery, we could remove those arcs. We could pre-solve the solution with a combined silo approach, so grouping silos together and solving it together. We could pre-solve the problem without staffing and simply add labor costs on the arcs. We could also use longer time steps. However, there's a trade-off there in terms of accuracy when you do use longer time steps. But the two ones in red that I'm going to go in here were the two parts of this problem that broke it down and made it solvable and were derived not from a mathematical deepening of the problem, but from a business understanding, and that's silo group formation and campaign shipping. With the successful speed ups being said, I want to make sure I tell you what the unsuccessful speed ups were, because I think when we share insights with each other, we too often like to share the good things and hide the bad things, but the bad things are often equally valuable to know when you're trying to solve the problem, what should you avoid? And I'm just going to go quickly through them because you get a copy of this deck, but the unsuccessful speed ups were slack variables on orders and closing profile constraints, shorter time steps, replacing arc timing maximum with a single arc usage, additional staffing constraints to remove staffing linking constraints between the individual members of staff, and those type of things just didn't work. in themselves, they feel kind of more mathematical. They didn't necessarily really use deep insights about the problems like the successful speed-ups did up higher. And we also had a set of potential speed-ups like network-based demurrage implementation, a staff jiggle after the no staffing pre-solve, so seeding that initial staff, and a rolling horizon instead of that 4-week window. However, this being a real-life project and us being given the task by the client, we have to decide and we need to look at the problem and understand what is going to give us the biggest bang for our buck. So at the end of the problem, we need to look and understand what 20% of work can we do to get 80% of value for our client, and really focus on those elements that are going to deliver value quickly and really leverage that business understanding that we've got. So let me start with the biggest insight that we had, again, from a business perspective. And again, if we hadn't gone out and been on site and talked to the client, this insight probably would not have happened. It wouldn't have been something that you'd automatically assume. And it was a silo grouping formulation. So we were able to group like silos together. And that might sound obvious, but it's not. In the actual, when you dig into the details, it wasn't clear that it's possible. And it was something along the lines of being able to group all of row 1 on the north side of the building together as a group of silos and manage that as a whole. And you get the same flow paths to get to and from silos in these groups. So you simplify that arc network, and you can get from any silo into this group to any other without having to worry about moving it around as part of the network optimization problem. And you resolve with all silos with extra constraints around flows to silo groups. So you imagine what we're doing is treating this almost like an island, and then we have the original problem surrounding that from the beginning. The impact, phenomenal. It dropped the number of silos of consideration from 260 to 20. And if you remember, the silos made out one of the largest parts of the variables that we had to consider. The other big part that wasn't quite as big was the commodity type, but we knew if we could do something here, then we'd also have a massive impact on the problem. The central parts, we had the silos, we had the time steps and the commodities. With the time steps, there's not much you can do. And mathematically, we did what we could and played around at different times. But we knew if we could apply business understanding to those two final bits of that variable equation, this is where it'd have the big impact, and that's what it did. So what we did is we treated the commodities as a single end product for the ship. So we treated order as a commodity type, not as each 0.1% of the underlying product. So it simplified it, and it reduces the number of commodity types and variables, but also the number of constraints. So we only need an assignment of product coming into the port to an order, so the final order leaving the port, what they've already got there ready, and a constraint ensuring all product assigned to an order by the time a vessel leaves blends to the correct specification. So this is really what we're looking at. We're just looking at the end of the day, we want to get a 10% protein content grain out to the ship, and in between, managing those 0.1% of each of those underlying products wasn't helpful. We needed to treat them as specific commodity types, and that reduced the problem from 100 to 20. So where did that leave us? Left us here. A massive reduction in the problem size. We went from 4.5 million variables down to under 900,000. Add on top of that a bunch of other speed ups that we've done and Flash Gordon's racing. So it was what basically turned the problem from something that's unsolvable into a solvable problem. It turned something that was quite challenging into something that we could deliver to the client within the specification, because the client required not only that we solve it, but we have a solution that can be computed in under 5 minutes. And there's a specific set of reasons for that that I'll delve into further on. But I want everyone in the audience to have a big takeaway from this. There's a really big takeaway. The takeaway is that the biggest benefit that we got out of this was making sure that we understood what the business side of this problem was, understanding the user, understanding how this problem looks like in real life. What are the issues? What is really there on the business end of the problem and not the mathematical end of the problem, because all that flowed through here to make a huge difference to our problem. Now, I can tell you right now, just changing those few things was a small amount of effort. Trying to play around with the time and change the problem to manage changes in time steps and horizons was a much more difficult thing mathematically. whereas these few changes were quite simple and in fact had the biggest impact. So it was a really eye-opening experience, and one that I won't forget, and that I like to remind people of. When you're doing your mathematics, when you're solving your problem, do not lose sight of the bigger picture and the strategy. Don't get stuck trying to optimize one small part of the problem, where if you took a step back and looked at the business problem and use that strategic understanding, you'll be able to make a much bigger difference than trying more and more to squeeze out a tiny percentage of difference from something that's potentially irrelevant. So what did it look like before we optimized? So how did the problem exist for them? What was their set of issues? What was the status quo before we came? Well, the status quo wasn't good, that's for sure. The status quo meant that the planners had operated at around 60% of their capacity, 60% of the optimal solution, which is 100% capacity utilization. That meant for a site with 12 million tons of capacity, 15 million tons of product moving through it, and 1 million tons of capacity, that they were losing 400,000 tons of that. There was a huge amount of wastage going on in terms of what they could or couldn't do. That was a bad situation to be in. It also meant that because the way they were running their systems, they had one row of planners with Excel sheets watched by a second row of planners with Excel sheets. So they weren't using the power of Gurobi. They were using the typical Excel way of solving a problem and looking at how can we manually try and intervene and manage this process. And there was an inability to respond to issues, and so they needed extra capacity and redundancy. And what that meant is, let's say a conveyor belt broke, or a ship didn't turn up, or something failed, the ship failed inspection, or fumigation didn't work out properly. They always required that additional capacity to be able to manually decide where the product was to go next. It was a huge challenge, and it was something that was costing the business. If you could imagine your business operating at 60% of its capability, that is a huge loss. That is one of the biggest gains that you could potentially make up, is increasing that percentage of utilization. So what did it look like after we put in the algorithm? Like this. After the algorithm was put in place and we began testing it, the planners began operating at 90% of their optimal solution. It opened up a whole window of efficiencies for them. If you think of the analogies with mining situations and a whole variety of other scenarios, if that port and that location is your bottleneck, by giving yourself 50% more capacity to deal with incoming products, it's a game changer. There's no other way to put it. It also meant that they gave planners at operational level more confidence. It was a huge advantage for them in looking at the way they needed to solve the problem, and if something went wrong, all of a sudden, instead of having Excel sheets that were clunky and difficult to use quickly, they had something that if something went wrong, they could press the red button, re-optimize the solution, and within 5 minutes they had an answer to their problem in terms of a vessel failing inspection or pest infestation or whatever it would happen to be. They had this amazing decision support tool at their fingertips to get them out of any bad situation whenever needed. So it gave them the power to react to day-to-day challenges, as mentioned. It really gave them that confidence to move beyond simply being stuck with a slow set of Excel sheets, a situation where you couldn't react to issues, and a lack of operational utilization of the silos to a point where there was a massive benefit in terms of what they could do. There was a lot less double touching of the products. That 60% of double movements of products was significantly reduced. But there was one more thing. There was one more thing that really blew their mind. And I'll show you what a client looks like when their mind has been blown. They look a little bit like this. On one of the test runs, they noticed, and this is a client's quote, that the algorithm decided to slow load a vessel towards the end. But we found that it was planning stop for the fourth ship down the track. So what we lost slow loading 4 hours at that point in time, we gained was 10 hours plus less grain movements down the end. And like him, their mind was completely blown and they couldn't believe what they saw. But I'll get off that slide so you don't go crazy looking at that looping and looping, and just draw the conclusion. I just want to say before we jump into the questions that the key takeaway here is sometimes when you're doing the mathematics, and I've been there, we've all been there, you can get stuck trying to solve a problem, and you can be challenged with the mathematics, and you can be challenged with the approach that you're taking and really trying to figure out how can I get out of this deep mathematical problem. My advice to everyone on this webinar is turn back to the business understanding, turn back to the strategy, turn back to the client's needs, and look at the problem again and understand it from another angle and understand how you can significantly simplify the problem to solve it in a new light. And I can tell you, in almost every single situation where I've been faced with a mathematical difficulty like this, and I've tried to go down a mathematical rabbit hole, so to speak, I've run into difficulties, we've run out of budget and had major issues. However, whenever I've turned around and looked at the strategy and understand and used the business understanding to reframe the problem, it's been a success, and the end solution's often been much simpler than the original problem.